into place on the other side of the room. It'll also need to be rotated, and this is easily done using the rotation handle. We'll place another 2 of these units in the facility to make a total of 4. Now we can add some UPSs to the project. They have no thermal impact as they're stored outside the facility, but these UPSs are required for the power network that we'll look at later. Adding 4 of these UPSs provides 960 kilowatts of power capacity to the facility. We'll close the library window now so we can look more closely at the room. Now we can add some power cabling to represent the obstructions from the PDU to the cabinets. These are normally under the floor, which we can make transparent so we can see details through it. Laying out cables is very easy. We'll choose the power cable object here to create the initial layout. Now for this room, we'll put the power cables above the cabinets. The default is for them to sit on the slab as this is most common, but it is possible to move them upwards. You can easily change the type and dimensions of this object to match your requirements. Now we need to add branches to the other cabinets and PDUs. We want to make the cable tray transparent so we can see through it for the rest of the model build. We've created a quick overhead closed conduit for the power cables, but this only represents the obstructions to airflow of the conduit. It is possible to make logical connections between pieces of equipment, perform power equipment failure analysis, and review how the power infrastructure is being used. But this requires the optional power module to be activated. I'll show you how easy this is with a model that has some IT equipment already installed. If we click to view the room summary, we see a view that shows various important metrics about the room in general, but we're going to focus on the power section. You'll notice this little icon is highlighted. That means the power module is activated. Because of this, the node Power System Information is present, and we can view a breakdown of the power network in the room. The top 2 figures show you how much power you have available and how much power you're using. Then you get a quick summary of the maximum loads on the main power equipment. You can see here that PDU-1 is drawing 192 kilowatts and UPS-1 is drawing 196 kilowatts. Under that is a summary of the power failure analysis. This shows you how many servers could fail if any one piece of power equipment was to fail, as well as the knock-on effect on other pieces of power equipment. Looking further down, we have the values of our current power draws from the utilities to give us an idea of how much power we use in total, including losses from all of the power equipment. The generator reports as having no power drawn from it because it's only used when there are problems with the utility supply. The final feature in the room summary provides an easy-to-understand efficiency summary. Power Usage Effectiveness, or PUE, is the first measure you'll see, and this includes everything excluding the utility losses, though you can add these if you want to. Then we have a breakdown of power usage and losses so you can see where your power is going. Finally, we have a report into how much energy you could save in kilowatt hours if you were to raise your room temperature whilst adhering to various preset and user set safety margins. Obviously, this can easily be converted into a monetary value if you know how much your energy costs. So, power information is available in the room summary, but you may want to visually inspect the logical power layout too. To look at the whole facility, let's open a power network view, which shows the electrical path from the utility all the way to each individual server. Here we can see the utility power supply, a generator and a switch to choose between the two. If we're interested in one piece of equipment, we can also view the network just at that point. We can see the two routes inside the facility that feed our server. In this example, if one PDU or UPS failed, the server would be able to take the load from the other branch. You can see here how the network would change if this were the case. Switching supplies should allow the server to survive this kind of failure. However, it's necessary to review the whole room to make sure this would be the case. To do that, we can open the Analyze Power Failure tool. This tool shows us a matrix of how the IT equipment would be left unpowered in the event of a power failure somewhere in the room. You can see here that if PDU-1 were to fail, for example, that no servers would be left unpowered. But if PDU-2 went down, we'd have 78 unpowered servers. If we then look at cascade failure, where the tool also considers the knock-on effect of the first failure on the rest of the power infrastructure, we can see that the total number of failed servers for the failure of PDU-1 would actually be 96. This is because any overloaded power infrastructure is also considered failed in this mode, so this room could do with improvements to the power network design. The Power Failure tool is valuable, showing you where improvements to your power network should be made. Obviously, all of the power usage figures heavily depend on the power that the IT equipment uses. We can take a look at this in more detail now. Here you can see a server close up, instantly recognisable as a Storage 3310. If we have a look at the power attributes of the unit, we can see the options available for configuring the power usage of this unit. Initially, we can decide whether to define the unit through power use and cooling air flow rate, a power and a delta T, or a flow rate and a delta T. Nearly all library items come with a preset power value, that is the nameplate factored by 50% to represent a fair amount of heat dissipation. You can also choose to set a typical value or a user set value if you know a particular configuration creates a certain amount of heat. Once you've entered these values, they're then saved, so you can switch between them as and when you like. The input power displays the total amount of heat created by the unit after factoring has been applied. With the next option, Power Source, we can specify how many power supplies the unit has and how they're configured. If we look at the back of the unit, we can see it has two power supplies, one on the left and one on the right. You can see they're both connected to supply A, and this is one of the reasons why so many servers failed in the analysis earlier. They're all double connected to the same power source. You can also specify whether the power load is shared between both supplies or switched in the event of failure. The two supplies configured in this cabinet are supply A and B, and here you can connect them to the power source, in this case PDU2 through fuse 1, and now PDU4 also through fuse 1. The power module gives you the ability to scale your power values to real data. It can be imported easily using the Scale Powers tool. It's quite common to know the real total load of the room through readings on PDUs. On the other end of the scale, you may even have power monitoring installed to the power strip level, so you know how much power is being used at each power strip in each cabinet. Whatever the degree of resolution, this data will at least ensure your total virtual facility load matches that of the real facility, and at best will make sure your heat distribution throughout the room is exact to the cabinet level,